Today we are going to learn about an algorithm, optimizing pathfinding with heuristics. We will explore how heuristics can enhance the efficiency of pathfinding in AI and robotics. You'll gain skills in choosing and implementing effective heuristics to optimize search performance. Welcome to our video on optimizing pathfinding with the A algorithm using heuristics. In this introduction, we'll touch on the basics of the A algorithm, a cornerstone in the field of computer science, especially in AI and robotics. Heuristics are key to enhancing the efficiency of this algorithm, serving as a guide to make decisions on the most promising path to take towards the goal. In this video, we'll not only define what heuristics are, but also delve into their practical applications, helping you understand their role in improving search performance. So, let's get started on this journey to master the use of heuristics in the A algorithm. In this segment, we will delve into the concept of heuristics within the framework of the A algorithm. A heuristic is essentially an educated guess that helps in decision-making processes, particularly in algorithms where a complete search of all possibilities is impractical. In the context of the A algorithm, heuristics serve to estimate the cost of the cheapest path from a given node to the goal. This estimation allows the algorithm to prioritize paths more likely to lead to an optimal solution. Unlike the true cost, which is known and calculated, heuristics provide an approximation, guiding the search process more efficiently. Common heuristic functions include the Manhattan distance and the Euclidean distance, each suited to different types of grids and movements. Understanding how and when to apply these functions is crucial for optimizing pathfinding tasks, making heuristics an invaluable tool in the realm of artificial intelligence and robotics. Let's explore the common types of heuristics employed in the A algorithm. The choice of heuristic depends heavily on the problem domain. The Manhattan distance, for instance, is widely used on grids where movement is restricted to horizontal and vertical directions. It's calculated by summing the absolute differences of the coordinates. In contrast, the Euclidean distance is ideal for scenarios where movement can happen in any direction, as it measures the shortest straight-line distance between 2 points. The diagonal distance is a variation used when diagonal movement is permissible and it factors in the additional cost associated with such movements. Furthermore, the octile distance is often used in grid-based pathfinding, similar to the diagonal distance but adjusted for costs associated with different types of terrain. Each of these heuristics has specific scenarios where they excel, and choosing the right one involves understanding the nature of the problem and the constraints of the environment. One of the critical challenges in implementing heuristics in the A algorithm is balancing accuracy with computational cost. A more accurate heuristic provides a closer approximation to the true cost, potentially reducing the number of nodes explored. However, increased accuracy often comes with higher computational demands. For instance, while the Euclidean distance provides a very accurate estimate, it is computationally more expensive than the Manhattan distance. The key is to find a balance that suits the specific requirements of your application. This might involve using a simpler heuristic that provides good enough guidance without overwhelming system resources. In practice, this balance is achieved by considering the environment's complexity and the available computational power. Effective strategies could include pre-computing certain values or employing adaptive heuristics that change based on the evolving state of the search process. Through strategic balancing, you can significantly enhance the efficiency of pathfinding algorithms. Selecting the appropriate heuristic for a given scenario is a fundamental step in optimizing the A algorithm's performance. The choice hinges on several factors, including the nature of the environment, the constraints of the problem, and the specific goals of the algorithm. For instance, in a grid-based game where characters move in straight lines, the Manhattan distance might be ideal. However, if the game allows for diagonal movement, the diagonal or octile distance might be more appropriate. It's crucial to analyze the constraints of the environment, such as obstacles and terrain types, to determine the most fitting heuristic. More complex environments may require a combination of heuristics or even custom-designed functions to meet specific requirements. Real-world examples include applications in robotics, where pathfinding must consider dynamic obstacles and varying terrains, necessitating adaptive or hybrid heuristics. By carefully evaluating each scenario, you can select the heuristic that best meets the needs of your pathfinding task, ensuring optimal performance and resource utilization. Heuristics have a profound impact on the efficiency of pathfinding algorithms like A. By providing a method to estimate the cost of reaching the goal, heuristics help prioritize which paths to explore, effectively reducing the search space. This reduction leads to significant efficiency gains, as the algorithm can focus on the most promising paths rather than exhaustively exploring all possibilities. For instance, in a game development scenario, implementing an effective heuristic can drastically reduce the time it takes for a character to find a path through a complex environment. Comparatively, non-heuristic methods, such as Dijkstra's algorithm, explore all paths with equal priority and can be less efficient in large or complex spaces. Case studies in robotics and AI demonstrate that well-chosen heuristics not only improve pathfinding speed but also reduce computational resource usage, allowing for smoother and more responsive applications. Understanding the impact of heuristics empowers developers to enhance their algorithms' performance and efficiency, leading to more effective solutions in real-world scenarios. In this case study, we will examine the application of heuristics in game development, a field where efficient pathfinding is crucial for creating engaging and immersive experiences. Game AI often involves navigating complex environments, requiring characters to find paths quickly and efficiently to maintain gameplay fluidity. Here, heuristics play a critical role in optimizing pathfinding algorithms. For example, in real-time strategy games, characters must navigate vast and dynamically changing terrains. Implementing heuristics like the Manhattan or Octile Distance can significantly enhance pathfinding speed and accuracy, allowing for more responsive AI. Optimization techniques such as pre-computed path networks or dynamic pathfinding adjustments based on game state can further improve performance. Practical examples from popular games illustrate how heuristics help overcome common pathfinding challenges, such as avoiding obstacles and navigating large maps efficiently. The lessons learned from these implementations highlight the importance of choosing the right heuristic for the context, as well as the need for ongoing testing and refinement to ensure optimal performance. By understanding these principles, developers can create more dynamic and engaging game experiences. Now, let's dive into a practical demonstration of implementing heuristics in code. We'll start by coding a simple heuristic function, such as the Manhattan distance, and integrate it into the AI algorithm. This step-by-step implementation will guide you through the process of defining the heuristic function, incorporating it into the algorithm's decision-making process, and testing its effectiveness. We'll use a basic grid-based environment to illustrate the implementation. As we progress, we'll discuss common debugging techniques and testing methods to ensure the heuristic functions correctly and efficiently. We'll also cover code optimization tips, such as reducing redundant calculations and utilizing efficient data structures to improve performance. By the end of this demonstration, you'll have a solid understanding of how to implement and refine heuristic functions in your code, enhancing the efficiency and effectiveness of your pathfinding algorithms. This hands-on approach will equip you with the skills needed to tackle real-world pathfinding challenges in AI and robotics. Testing and refining heuristics is a critical part of optimizing pathfinding algorithms. Effective testing ensures that the heuristic functions are performing as expected and identifies areas for improvement. Begin by setting up a test environment that mimics real-world scenarios where your algorithm will be used. This could include varying grid sizes, obstacle densities, and movement constraints. Techniques for refinement involve iteratively adjusting heuristic parameters, such as weights or scaling factors, and observing their impact on pathfinding performance. Be aware of common pitfalls, such as overfitting heuristics to specific test cases, which can lead to suboptimal performance in other scenarios. Iterative improvement involves continuously testing and refining the heuristics based on feedback and results, gradually enhancing their accuracy and efficiency. Examples of successful testing practices include using automated testing frameworks to validate heuristic performance across multiple scenarios and employing visualization tools to analyze and debug pathfinding behavior. By adhering to these best practices, you can ensure that your heuristics are robust, efficient, and well-suited to the challenges of real-world pathfinding tasks. As we conclude this video on optimizing pathfinding with heuristics in the AI algorithm, let's recap the key concepts we've covered. We began by defining heuristics and their crucial role in improving the efficiency of pathfinding algorithms. We explored various types of heuristics, such as the Manhattan and Euclidean distances, and discussed how to balance accuracy with computational cost. We examined the impact of heuristics on pathfinding efficiency through real-world examples and case studies. You also learned practical skills in implementing heuristics in code and refining them through testing. By understanding these concepts, you're now equipped to apply heuristics effectively in AI and robotics projects. Remember, the journey of learning doesn't stop here. We encourage you to further explore the fascinating world of heuristics and pathfinding, continuously refining your skills and expanding your knowledge. Thank you for joining us, and we wish you success in your pathfinding endeavors.